we are going to be talking about linear equations. Linear equations. Linear equations have two variables, and they produce lines when you graph them. See that word? Line, right? In that word linear, they make a line. And two variables. Now we're used to equations that look like this. Right? How many variables in an equation like that? One. So we're going to be looking at equations that have two variables. So here's the standard form of a linear equation. We can write linear equations in several different ways. This is one of them, and we call it standard form. AX plus BY equals C. There's a lot of letters going on there. How many variables does it look like we're dealing with?
3, 5. You know X and Y are the coordinate things. Like X and
Well, what's going on here? I heard 3, I heard 2, I heard 5. What do you think?
I know.
How many do we see? How many variables? How do we see 6? 1, 2, 3, 4, 5, maybe 5. It is 2. The X and the Y are the variables. So what is this A, B, and C? The A, B, and C represent placeholders for values. Now I know some of these, right? X and Y, they kind of do too. But it's basically a format. So if I see something in this format with numbers in the place of an A, B, and a C, I know I have a linear equation. So for example, 2x plus 5y equals 8. Does this follow ax plus by equals c's format? So what's A? Yeah, what's B?
5.
And what's C? So what this means is if you see stuff that looks like this in that format, something times x plus something times y equals a number, you have a linear equation. And it's in standard form. And once we learn about other forms, maybe standard form will make more sense. But if you graph this, you get a line. Now how do you graph something with two variables? Well, you have to understand how solutions work. Now solutions with one variable, how do I find the solution with one variable? Like how would I find the solution to this? What would I do first?
You subtract 3 from both sides.
I subtract 3 from both sides and I get this, right? Subtraction, property of equality, and then what?
You divide 3 from both sides.
Right. I use the division property of equality to divide both sides by 3x equals 2. Now what does that mean that x equals 2 is the solution? What does that mean?
When you just particularly X and put in the 2, you'll get
Exactly right. If I plug this back in, if I take this and plug it in for the x, and remember we had a little process for doing that. You would plug it in, and then this kind of became a question. Does this side equal that side? And then we would work it out. And even though we saw it kind of work, we still did number compared to number. Remember that? So we're going to do the same thing, but with two variables. But now I've got an x and a y. So one solution to this equation here, we're talking about this one up here, is -1, 2. I'm telling you this. So now you should be saying, well, how do you know that's a solution? How can I show that this is a solution to this? Well, how did I show this was a solution to that? Plugged it in. So what am I going to do here? Plug it in. But plug what in? Well, x, y pair. This one's x, this one's y, right? So I take my 2x plus 5y equals 8. Now I'm going to kind of make it like a question. When I replace the x with -1 and the 5 with 2, do I get 8? Right? Because x is -1 and y is 2. So let's see. -2 plus 10. Does that give me 8? And you can probably see already that it does, but just like with the above, you always do number compared to number. So is -1, 2 a solution to this equation? Yes. Yes, it is. And we prove it just like we do if there was only one variable. You plug them in, and you should get a true statement when all is said and done. Right? This is true. 8 is 8. It works. Are there other solutions to this? Can I have this? How many solutions are there to this one? This one, right? X equals 2. I don't think we can find anything else. But is there another? And let's try this one. I'm going to give you this ordered pair. Is it a solution to 2x plus 5y equals 8? How can I tell? This one's x, this one's y. Let's plug it in. 2 times x plus 5 times y. Does that give me 8? Well, that's 8, and that's 0. Well, what's 8 plus 0? That's 8. So it works. So here's just another solution. We haven't seen that before. We haven't seen that before. Let's look at another example. Maybe we can come up with how we get more than one solution. So I've got a new linear equation here. It's right here. Does it follow the format ax plus by equals c? No or yes? Well, let's see. Well, what would a be? What about b? Is it 1? This is a plus, this is a minus. So what's going on here? It would be 4.
Negative something.
It would be negative 1, because remember that my invisible coefficient is there. I'm adding negative 1y. And then what's my c? 7. So this is actually following that format. It's just when we say here's ax plus by equals c, is that equivalent to minus y? This thing here? Yeah. So we kind of just condensed it already. Yes? Because look at this, 3x minus y. That's the same as 3x plus a negative 1y, isn't it? Because what's a positive negative? That's a negative. 1 times y is y. So we always write things in the simplest form, but we also sometimes have to be able to step back and see where it might have come from. And so it did. It came from adding a negative 1 times the y. So when you see a negative kind of coefficient, your b might be negative, or your a or your c. It could be negative. But I guess we're getting back to the main point. Is it of that format? Ax plus by equals c. It is. So this is a linear equation. If I was to graph it, I would get a line. But now I want to test my solutions. It's a 3, 4. Let's see if it's a solution to 3x minus y equals 7. So how would I test that out? Here's my x, here's my y, right? Plug her in. Yeah. So 3 times 3, my y is 4. And now it's kind of a question. Does that equal 7? So I'm getting 9 minus 4. Does that equal 7? Well, 9 minus 4 is 5. Is that 7?
No.
No. So is this a solution? No. If you don't get a true statement, then it's not a solution. That's all that that means. Let's see if 1 negative 4 is going to be a solution. Again, I've got 3x minus y equals 7. My x is 1 minus, what's my y? Negative 4. Be careful with the negatives, because we are going to plug in the negative. It doesn't affect that sign. But when I have a negative and a negative, what do I have? A positive, right? So this becomes 3 plus 4. At least I should put my little question marks in. Is that 7? Yes, it is. So is this a solution? It's a solution. So I found a solution. Is it the solution, or are there others? Let's try some other points. Let's try 2, negative 1. So again, I've got 3x minus y equals 7. I've given an x of 2, and I'm given a y of negative 1. Does that equal 7? So again, be very careful when you have negative x's or negative y's. 6 minus minus 1, what's this that the same as? Plus 1. And that is 7. So is 2, negative 1 a solution to this linear equation? That worked. Let's try 3, negative 2. So 3 times 3 minus the y, is that 7? Well, let's see, that's 9 minus 2. Is that 7? It sure is. So what else do I have? 3, 2 is a solution. How about 4, 5? 3 times 4 minus 5, is that the same as 7? 12 minus 5. Is that the same as 7? And it is. Look at this. So far, I've got 4 solutions. Only one wasn't. So, are there other ones? Can I find other solutions? What? Can you think of one? Do you have a question? y equals 7?
Oh.
Yeah, I'm using this particular linear equation. So, can we think of other solutions? What do you think? 10, 11 doesn't work? How will I know if this is a solution? Let's plug it in. The only way I can do it, right? Does 3 times 10 minus 11 equal 7? 30 minus 11, is that 7? Oh, no, it's not. So, where's that 19? So, no. That one doesn't work. So, we can't just randomly pick stuff, right? It's not everything. But can we think of another one? You got one? Okay, so what do you want? What's my coordinate pair? What's my xy pair that you gave me? 5 and 8. Let's see if it works. So 3 times 5 minus y, so that's 8. Does that equal 7? 15 minus 8. Does that equal 7? It sure does. You got another one.
What about 6, 11? 4,
What about 6, 11? Does that one work? Let's try it. 3 times 6 minus 11. Does that equal 7? 18 minus 11. Does that equal 7? Well, what's 18 minus 11? So it looks like 6, 11 is another one. So how are you coming up with them?
0.
How are you coming up with them?
Yeah, 3 to the
You add 1 to the, you do what? What number? So you pick any number and you add 1? I think you multiply it by 3 and then you subtract 7. That's what you do. Is that what you do? I don't know. So, but there is a rule, and you're absolutely right. We can come up with a rule to create them. How many can we create, do you think? A lot, how many? There are an infinite number of these. And why is that? Well, there is an infinite amount of numbers, but, you know, this equation that we did, there's an infinite amount of numbers, but there's only one solution. So how come when I'm doing these, you're telling me I can do this all day and come up with solutions, right? Yeah, I think he's got a whole bunch. You can come up with, right? So what's going on here? Now remember what this is. It's a linear equation. If I was to graph these points, I'm going to find a little space here to graph them. So what points do I have? I have 3, 4, 5, 8, 6, 11. What else did I have here? 2, negative 1. What's happening here? I'm getting a line. And you know what's on these lines? Ordered pairs. And you know what? Every ordered pair on this line, guess what? You plug in all these ordered pairs, they work. They're all solutions. So a linear equation graphs a line where every point on that line is a solution to the equation. You plug them in, it works. So if I want to know if a point is on a line, and I'm given this equation, all I have to do is plug it in. If it works, the point is on the line. If it doesn't, the point is not on the line like this one. 3, 4 is not on this line because it doesn't work. Yeah. So graphing is really giving us a solution set. It's giving us a set of solutions to an equation, a linear equation in 2 variables. So the graphing is actually kind of important. So we're going to actually be looking at 3 different methods for graphing. Not today. Today we're just going to look at one method, and it's one method you're familiar with. But we're going to just kind of bring in the domain and range again. It's just really think about what we came from and where we are now. Graphing represents the set of points in a coordinate plane that represent all the solutions to an equation. So every point on the line is a solution to the equation. So we're going to work with the table of values method. Didn't we do this already? Yeah, we did this a couple of classes ago. Yeah. Now what's the twist? Not really a twist. Well, we're playing with domain now. Now when we did this a couple of days ago, I said, here's the domain, and I gave you some points, whatever they were. I don't remember what they were, right? And then we just worked with these 3 points, or however many points I gave you. What's our domain going to be now? All real numbers, unless you're told differently. So the domain is all real numbers, unless you're told differently. So how does that affect our graphing? Because remember what we did with this? We would make our little our domain is all real numbers, how do I make a table where I've got all real numbers in it? How am I going to do that? How many real numbers are there? Yeah, we can't write them all down, right? So what are we going to do? We are going to use the fact that if you're graphing a linear equation, what does it look like? A line. So if I graph some of the points, can I kind of see what my line is going to look like? And then kind of fill in the rest of this. So what am I going to put in here? A sample of the domain. Just some of the points. And then for those few points that I come up with, figure out their their outputs, and then we'll come up with a line. So let's look at an example here. This is on the bottom of page 1. Hopefully we can follow along here. I want to graph this linear equation, y equals 2x plus 3. And so the first thing I want to do is make a table of values. Now, does it say what the domain is? You see it? Does it say place domain is? Where? Where do you see domain? No, this is not a domain. This is just a table of values. What is the domain? It should say graph the equation on domain whatever. Does it say that? When it doesn't say, what should we assume the domain is? All real numbers. If it does not say, we want all the numbers. I want to see what it looks like for all the numbers. Well, I can't possibly make a table with all the numbers, so I'm going to take some of them. I could choose any real numbers I want. Some good numbers to choose. Excuse me. A couple of negatives, 0, and a couple of positives. So this is not a bad set of numbers to try if you're graphing using the table of values. I'm going to put my rule a little bit closer so I can see what it is. So to put, if my x is -2, what's my y going to be? What's 2 times -2? Plus 3. Right? Okay. So let's try it for 2 times -1 plus 3. So it's -2 plus 3. 1? Let's see. 2 times 0 plus 3. That's 3. The 0 is always easy, right? Because it kind of blocks out that. You're just left with that guy. Let's see. 2 times 1 plus 3. 5. And 2 times 2 plus 3. That's it, okay? So is my domain -2, -1, 0, 1, 2? And my range -1, 1, 3, 5, 7? No. This is just a sample. This is some of the domain. This is some of the range. Now I'm going to go ahead and graph them. We've done this before. So -2, -1, -1, 1, 0, 3, 1, 1, 2, 3, 4, 5, and 2, 7. Now before, I had asked and I said, gee, do we connect those points? And the answer was no, remember? I said, don't connect the points. Except now I'm saying connect the points. Why? Why am I being so confusing? Well, just because it's what I do. But why am I connecting points here? I want the numbers in between this time. Because what's my domain? What's my domain? All real numbers. By connecting the dots, I'm saying, you know what? The pattern continues beyond the sample of points that I graphed because I understand how lines work. That these, now I have every point. I have graphed every solution. Because what do these arrows mean? Infinite. Right? It extends forever this way and that way. This is a line that goes infinitely in both directions. So are the arrows important? You betcha, right? If you don't have the arrows there, you have not represented the domain of all real numbers. Now what's my range? The range is also all real numbers, right? That's going this way. So kind of using our domain and range. So when it's all real numbers, this is not your, these are members of your domain, but it's not the complete domain. We're just doing a sample so that I can see what the pattern is and I can see what they look like. Makes sense, not make sense. Makes sense, thumbs up. Okay? Not making sense, that means thumbs are down. Question. Where am I losing? No, they didn't vote. Who's sleeping because we just had lunch? Okay, wake it up. domain is all real numbers. Now, I can't graph all real numbers, so let's take a sample of those numbers. What are good ones to try? Yeah, we want to pick something that makes it easy, right? Keyword, easy. So are you going to pick 1.5 million? No, easy numbers. And what are we doing with the numbers? Well, you multiply them by -3, and then you add 1. So what's -3 times -2 plus 1? -3 times -2, 6 plus 1, 7. -3 times -1 plus 1, 4. Zero's easy, right? What do we get when we plug 0 in? 1. -3 times 1 plus 1, -2. And then -3 times 2 plus 1, that's -6 plus 1, -5. All right, we go ahead and graph this. So we get -2, 1, 2, 3, 4, 5, 6, 7, -1, 2, 3, 4, 0, 1, -1, 1, 3, 4, 5. So I've graphed my sample points. Can I see my pattern now? Can we see the line that's forming? Yes, we can, so I can now connect my points. Carefully. Are the arrows important? If you don't put the arrows in, are you incorrect? Yep. That's right. Should I mark you wrong? Yep. Okay. My domain is all real numbers, or all real numbers represented in this graph. Yep. Is it a function? No question here. Yes. Yes, it is. So what do you think? Easy or hard? Right? It's what you've done, but I just want you thinking about it a little bit more. Not just blindly, yeah, connect points, don't connect points. I just want you to think about it a little bit more. What's my domain? That's why I'm connected. Well, look at this little function here. Or if it's a function, right? We don't know yet. It's an equation, y equals 3. And I want to graph that. Graph y equals 3. Wow. Well, let's see. Does it follow ax plus by equals c? Let's look at it. What's a? I don't see anything. What's a? Wait. Just let me answer this question first. Is it going to be a line, right? Or is it just a dot? Like, what is that? So if it's like this, it's a line, right? That's our rule. This is a linear equation. What's a? You see an x here? How do you get it? I don't see an x here. So what was a? I don't know either. We'll come back to that. What's b? What's the coefficient in front of that y? That's invisible. 1. What's c? So what was a? 0. Because what's 0 times x? That's why it's gone. So in its weird way, this does follow ax plus by equals c. It's going to be a line. So I don't see domain anywhere, so it must be I want the domain of all real numbers. So let me take a sample of the real numbers. -2, right? These are my favorites. Sometimes maybe I want different ones, but that's what I want now. And let me plug it in. Well, plug it in. Plug in what? Do you see x here? -2. Y is 3. It's just like answering the question. -1. X is negative. Y is 3. X is 0. Y is 3.
Okay. Trying to see a pattern there.
Yeah, so let's graph these points.
That's all right.
-2, 1, 2, 3. -1, 3, 0, 3. What's happening?
It's in the formation.
Well, they're all straight lines, but what's interesting about this straight line?
Showing a profit.
Yeah, what do we call lines that go left to right? Horizontal. This is kind of a big deal. See how I'm writing this down? See how I'm kind of like circling? This is important. This would be a place where you put in stars and exclamation points. Y equals 3. How about, what if I had y equals -2? What do you think that would look like? Where would that be? That would be down here, wouldn't it? Wouldn't that be y equals -2? Look at all the points on this line. Aren't there y values -2? So, whenever you have y equals a number, a constant, it's a horizontal line. For some reason, this is difficult for students. I don't know why. I think it's because you see why you want to go up and down. But it's a horizontal line. Now let's try, and is it a function? It sure is. Let's try this. Look at that, x equals -2. Now other, this is gonna be a line. My A is 1, my B is 0, my C is -2. So let's do the same thing. My domain is all real numbers, I guess, right? But, so let me write them down. -2. Wait, I can't control my hands. I know I should be writing -1, 0, 1, 2. Why am I not doing that? What's happening? It's shouting at me, X is -2. I don't care what you say, X is -2. Does it give me any information about Y?
No.
Then I don't care. Pick anything you want for Y. And then let's graph this.
Any number you want.
Yeah. Now, you don't want to pick a dumb number. You want to pick a number that's easy to graph. And what happens? What happens?
It's vertical.
Vertical line. Look at that. And now, is this thing a function? No, not a function. Well, we have an input with more than one output. Now, the domain pretty much wrote itself. What is the domain of this thing? -2, that's it. My range is all real numbers. So this is vertical. Trust me when I say this will become confusing at some point. I hope not, I shouldn't say that. But a lot of people find this confusing for some reason. If I'm giving you X equals a number and you forget what you're supposed to do, make a table, put in that number here, put anything you need to there. Right? Regraph it if you're having trouble remembering that Y equals a number is a horizontal line, and X equals a number is a vertical line. Okay? Limiting domain. Now, we limit domain sometimes because we don't always want all real numbers. What if I'm working with an X value and it's time? I'm rolling a marble or something, right? Time increases. Is time negative? So, I don't always want all real numbers. Sometimes I don't want negative values. So we sometimes will give a domain that's not all real numbers. So how do you do that? Well, what points do you pick here? Well, I would pick 0 because that's a boundary point. Am I going to pick 1? Look at my domain, x less than or equal to 0. Should I pick 1? Not my domain. So pick numbers in your domain. Find the y values, and I'm just plugging these in. Hopefully I'm doing it right. I'm just going a little bit faster here. I just plugged my x's into here, and then I go and I graph it. Something's not right. This goes up here, that's right. Right? And then I connect it. Well, watch how I'm connecting the values. Am I making a double arrow? Why did I not make a double arrow when I graphed these points? Why not? Yeah, I don't have any domain over here. No domain. So I'm putting it full stop here because this is a domain of 0 and smaller, right? We've seen that. And then my range is going to be what? Y bigger than or equal to -3. Right? And this is just from practicing a domain and range. Okay. Now this other one, you're going to do the same thing. Pick it with 1, but look at the other points that I picked. First of all, are all these numbers 1 or bigger? Are they in my domain? And why did I pick 2, 4, 6, 8? Why?
Because even numbers are easier to have.
Yes. So when you choose your domain, choose wisely. I'm going to let you guys work on this one. See what you get while I give you the homework. Here, let's just quickly look here. I filled in my table, right? Look at the graph. Do I have a domain bigger than 1?